Hello everyone. Welcome to the series of MOSFET amplifiers. So in this video, I'm going to calculate impedances seen at different nodes of MOSFET. Because it is very important to calculate the impedances at different nodes so that we can use this particular thing while calculating gain. Okay, so I'll take simple NMOS. So if I take simple NMOS, so yes, this is your drain terminal. Let's simple see. Yeah, this is your drain, gate, and source. So the point is that suppose we want to calculate the impedance seen from this drain side. Then how to calculate it? And if you want to see the impedance from the source side, and if you want to see the impedance from gate side. So what will the calculation strategy for that? So if I'm calculating from the side of drain, and let's suppose this gate is connected to ground and source is connected to ground, and what we will see here. Okay. So if I want to calculate the impedance from the side of drain, and let's suppose the source is ground and gate is ground. Okay. If these two terminals are grounded and you want to calculate the impedance from the side of drain. Then basic concept of impedance calculation from any point, you need to consider test source. This test source is your Vx. Suppose this test source is your Vx, and current flowing across it your Ix. Then the impedance on this side or looking from the drain side will be nothing but this RD, not D, R out I can say. So this R out is nothing but Vx by Ix, keeping all the sources zero. So I connected this gate to zero, source to zero. So if we calculate this impedance, then we need to use a small signal model. So if I want to use the small signal model, here your gate is grounded, here the source is grounded. So this is nothing but GMVGS. And suppose no channel length modulation and other thing is there. So okay, now without channel length modulation, I think this is not easy to calculate here. Suppose a channel length modulation parameter is also there. It can also be calibrated for that case, but if I'm considering suppose R naught also, this is Vx and this current is Ix. So yes, this is your VGS. This is your VGS. So if I apply KVL from this side at this drain node, if I apply KVL this drain node, and what you'll get? Ix is equal to GM VGS plus drain voltage minus source voltage divided by R naught. So drain voltage is nothing but Vx minus source voltage 0 by R naught. In this case, your VGS is nothing but a KVL from this point to this point. So this VGS is 0 here. VGS is 0 here. So Ix is Vx by R naught. So here the ratio Vx by Ix is R naught only. So this R naught means intrinsic impedance of this MOSFET is itself the output impedance when we look from the gate side, sorry, drain side. So why I said this, if R naught is not given, then this impedance is not too easy to calculate, but I think it can be calculated. This will be like if this R naught is not given, then it can be calculated, but it will be infinite. Means in that case, if the R naught is not there, then Ix is what? Simply GM VGS. If GM VGS is there and VGS is 0 in this case, so Ix will be 0 and your Vx versus Is. So Vx by Ix is a thing but infinite. So if R naught is not given here, then it will show the infinite impedance from the side of drain. So this is how to calculate the impedance from the side of drain. Now calculate the impedance from the side of source. In this particular, if I calculate this impedance from the side of source, so this is your source terminal, and this, suppose this drain is grounded and your gate is grounded and R naught is considered. Let's suppose R naught is considered. And if it is not considered, then I'll tell you later. So if this is your test source, Vx, and this is Ix. So now, either we can draw the small signal or the intuitive analysis that I shown for the voltage gain can also be used here. But for now, I'm using the small signal. Gate is grounded. Here your GM, VGS, and here R naught is there. Yes, body effect can also be considered, but I'm leaving it for now. So this is a 0. Now we have taken the test source here. This test source is Vx, where the current is Ix. So if we apply KVL at this node or KCL at this node, then Ix is nothing but Ix is minus GM-VGS plus this source voltage minus drain voltage, which is nothing but Vx minus 0, because drain voltage is 0, divided by R naught. This is your first equation. And second equation we will get from this side, KVL at the input side. So this equation is from KVL from this side. So here we can write 0 minus VGS minus Vx is equal to 0. This is second equation. This is second equation. From second, we'll get VGS equal to minus Vx. Put this value of VGS inside the first, we'll get Ix equal to GM Vx plus Vx by R naught. So if we take Vx common on the right hand side, the Vx, then Gm plus 1 upon R naught will be there. So the ratio Vx by Ix is nothing but 1 upon Gm plus 1 upon R naught. So this is the impedance when we look from the side of source. So if lambda is 0, means no channel length modulation is there, means R naught is infinite. In that case, your this Vx by Ix will be 1 upon Gm. So in the simple model, when we look from the side of source, we have the impedance 1 upon Gm if channel length modulation is not considered, and it is 1 upon Gm plus 1 upon R naught if CLM is considered. So if we are looking from the side of gate, it will always offer the infinite impedance. You can see this thing, because when we look from the side of gate, there is a zero current flowing through this, because open gate oxide is there, due to which no current flows across it. So if whatever the test source we apply from the gate side, we'll get the Ix is always 0. That's why this Vx by Ix is infinite from the side of gate. This is infinite. So Rg is always infinite. So I calculated here from the side of source and drain, and it is infinite from the side of gate. So if we want to consider channel length body effect also, we can consider here. And suppose body effect is also considered. So yeah, this is your, we can also consider the body effect, no problem in that. Suppose I am considering from the side of drain, and this source is at some potential. Let's suppose the source is at some potential, not 0. If the source is at some potential and body is connected to ground, and if we want to calculate the impedance from the side of drain, we can apply a test source here, and across this test source, we can consider the Ix current, and we can apply the small signal here. So the extra terms will come here, like R naught will be there, and GMB BVS will be here. So this current source and this R naught will be extra. The other term is GMVGS. This is going to come here, GMVGS. So when we'll calculate here, we'll get the expression for Vx by Ix, which is nothing but the impedance is looking when we look from the side of drain. Okay. So in this way, we can calculate the impedance looking from the side of drain or side of source. It is important. Now, if I consider some special structure, like this is your source, this is a gate, this is a drain, and a gate and drain are shorted. This is called diode connected device. This is called diode connected device. Diode connected device. In this, if we draw the small signal, if we want to calculate the impedance from the side of drain and side of source, it is always infinite when we calculate from the side of gate, so no need to calculate it. But if I calculate from the suppose drain side, so now draw the small signal. So the small signal gate, source, and drain. So this gate is grounded. Obviously, this gate is grounded, and this source is grounded. This is your VGS, and this is your GMVGS, and let's consider R naught, and this is your drain, and here we are applying the test source because we are calculating the impedance from the side of drain. So it is IX. Okay. So in this, we are saying that gate is connected with drain. So just make it short. Just make it short. So this is the small signal for this structure. And if I want to calculate here the ratio of V out by, sorry, Vx by Ix, we'll get the expression for the output impedance, or can say impedance from the side of drain. So this is the impedance. This is nothing but Vx by Ix. So simply write the KVL here. So one very common thing is here that this VGS is 0. Okay, so this, yeah, from this input KVL, this VGS is, yeah, this VGS is looking 0. From the input KVL, this VGS is looking 0. But we can see that by making this short, this VGS can be calculated from this side, this KVL. Then we'll get Vx minus VGS is equal to Vx minus VGS is equal to 0. So we get VGS is equal to, actually in this case the gate is not grounded. If this DC voltage is here, it will be grounded. But due to the short, we consider that this terminal is directly connected to drain. So there is no meaning of this ground. So we consider that this gate is shorted with drain. So here we cannot make ground actually. We are simply considering that gate and drain are shorted. So if you are making it ground, it will create the problem because Vx, we are taking the Vx at the drain. So this VGS is nothing but a Vx. And if we apply here the KCL, and that KCL is like Ix is equal to GM plus drain voltage minus source voltage divided by R naught. Okay. So from here we'll get Ix equal to GM, and Vx is equal to nothing, VG is equal to Vx. So GM Vx plus Vx by R naught. So from this expression, we'll get Vx by Rx is equal to 1 upon GM plus 1 upon R naught. So if channel length modulation is not considered, if lambda equal to 0, we'll get Vx by Ix is equal to 1 upon Gm. So this is Ix. Okay, Vx by Ix equal to 1 upon Gm if lambda equal to 0. So similar thing, if you want to calculate the same thing for this particular device, so if this gate and drain are shorted, so yeah, this was a mistake that you cannot connect it to ground. Gate cannot be connected to ground because it is shorted with drain. So suppose now this drain is grounded and you want to calculate the impedance from side of source. So this Vx is nothing but a source, that is DC source. Yeah, this is your Vx and this is Ix. Okay. So now in this case, if we apply the small signal and we calculate the particular, again you can see that this is your gate, and the gate and drain are shorted and drain is your grounded. So here we have GMVGS current and here the R naught. This is your GMVGS. So yeah, this is your GMVGS. This is your Vx, and this gate and drain are connected. And this source is nothing but consisting of Vx, or the source we applied here. Okay. So if we apply KVL here or KCL here at this node, we will get the expression for Vx, or sorry, Ix. You will get the expression like Ix is equal to, yeah, Ix is equal to minus GMVx minus GMVGS plus Vx, that is source voltage, minus drain voltage divided by R naught. So this is the KCL, and you can see this KVL. If I am looking at this KVL from Vx to, not, oh, this is not Vx, this is VGS. So if you are looking from this KVL Vx to this ground, we are seeing that this VGS is nothing but equal to minus Vx. So from here, I'll get again the Ix equal to GMVx plus Vx by R naught. So again, also we are getting the same expression I am writing here. So from here also I'm getting Vx by Ix equal to 1 upon Gm plus 1 upon R naught. So when lambda equal to 0, this R source, or can say Vx by Ix, is tending to 1 upon Gm. So yes. So when we are looking from the side of drain or side of source, from either side we are getting 1 upon Gm impedance if it is a diode connected device. So yeah. So if it is a diode connected device, we are seeing the impedance, same impedance, 1 upon Gm. So these concepts are very important when we use this device, diode connected device, in between for calculation of gain. I will use this expression of impedances. At that point of time, I may calculate or I may directly use. So this is enough for this video. So thank you.